Hi guys, and welcome to another lesson. In this lesson in data management with Python, we are going to talk about analyzing the data with Python. And once you have a set of data, you usually want to ask questions about it. For example, in the lending library example, you might want to know the total cost of the items or even the average cost of an item. You might want to know who contributed the most items, which items are out on loan at any given time, and so on. You can do that thing using Python, and you could write functions using all the standard Python features that would answer those questions. However, Python has some powerful features that often get overlooked that are especially useful for analyzing data sets. So in this section, we'll look at some of the built-in features we can use, especially the functional programming features of the language. We then turn our attention to the itertools module, which offers more advanced features that often save time and computing resources when compared with the standard alternatives. So we'll look at itertools a little bit later in this exercise. But first we'll start analyzing data using built-in features of Python. When you analyze data, it is important to select the right data structure. For example, Python includes a set data type that automatically eliminates duplicates. If you care only about unique values, converting or extracting the data to a set can simplify the process considerably. Similarly, using Python dictionaries to provide keyword access rather than numeric indices often improves code readability and thus reliability. And we saw that in section 2 where we compare the CSV dictionary-based reader with the standard tuple-based reader. If you are finding that your code is getting complicated, it is often worthwhile to stop and consider whether a different data structure would help. In addition to the wide variety of data structures, Python also offers many built-in and standard library functions that we can use, such as any, all, map, sorted, and also slicing. Slicing isn't technically a function but an operation. However, it does return a value in a similar way that a function would. When you combine these functions with Python generator expressions and list comprehensions, you have a powerful toolkit for slicing and dicing your data. So we will apply these techniques to our lending data, the data for our lending database, to answer the question it's raised in the opening paragraphs of this lesson. I will try that now, and you can use the file that is called lending data in the archive .rar packed zipped file. There are two files in there in the folders that is named similarly. It's called lending. I think it's called lending. Let me see. Lendy data. It's called Lendy data, but use the file that is called lending underscore data. That is the file that we are going to use, and I've already prepared this file, and it's already also linked in the lesson as a separate file. So just use this file for this lesson. So let's now try to use standard Python features to answer the questions about the LendyDB data. Like, what is the total cost of all items? What is the average cost of an item? Who contributed the most? Which items are currently on loan? So when you have your data loaded, this file loaded, lending underscore data, and be in the correct remember, it should be in the same working directory from where you're starting your Python prompt. So let's start. Like always, I will explain at the end what's going on. Let's do this one. So what we just did here is to answer what is the total cost of all items. And to answer the question what is the average cost of an item, we'll use this function or this code. There is a parenthesis too much here. So to answer the question, who contributed the most items? Indentation should be. some logic error almost. And to answer the question, which items are currently on loan? Let's define another quick function. When we are just testing some quick codes, so you can use the way of just structuring this code this way, but in production code it should be much more intuitive to Pythonic way of doing things. Just a typo there. So let's go over this code a little bit now. So we started by creating a Python module containing our sample data and importing that data into the interpreter. That's from lending_data import all. Note the handy trick of using the first entry, having index 0 in each data section to store a list of that section's field descriptions. This has two useful effects. Every ID value of any given data section of the three sections now matches the 0 relative index of that same row in its section. For example, the Mike row of the members data section having an ID of 3. Zero, 1, 2, 3. 1, 2, 3. That's the index, but it starts with 0. You have access to the field names both programmatically as an aide-de-memoire in the interpreter by accessing the first record. The downside is that in your processing code, we must remember to adjust by 1 the length. That's hence -1. And indices of the data sections to account for the extra header line record for each section. We then used standard Python tools to answer several questions about the data using standard Python tools. For each question, we defined a smaller helper function that typically just extracted a field from a data entry. For that first question, it returned the cost as an integer value by extracting the string value and stripping the $sign from the front before converting to an integer. We then use Python's built-in sum function applied to a generator expression to calculate the total cost of the items. And we then computed the average item cost by dividing that total cost by the number of items. To find out who contributed which item, we defined a function owner that simply extracted the owner ID field from an item record. We then looped over all the members, checking how many items each member owned. Finally, we determined which items were out on loan by creating a helper function called onLoan that returned a Boolean result depending on whether or not the date return field was null. We then used this in a list comprehension with a filter condition using the onLoan function. So in this example, we saw that we can use the built-in functions and data structures combined with loops and generators to answer most questions about data. The problem is that for volumes of data, these techniques requires storing large lists in memory and may involve looping over those lists many times. This can become very slow and resource intensive. The Python itertools module provides several functions that can reduce the loads significantly. I will look at that now. And like we talked about, the itertools module of the standard Python library provides a set of tools that utilize functional programming principles to consume iterable objects and produce other iterables as results. This means that the functions can be combined to build sophisticated data filters. Before looking at how itertools can be used on the lending data, we should look at some of the functions provided using simpler datasets. These functions are powerful but operate in slightly different ways than most of the functions you have dealt with in the past. In particular, they are all geared around processing iterators. And you should recall that all the standard Python collections, as well as objects such as files, are iterators. We can also create our own custom iterators by defining some methods that adhere to the Python iterator protocol. The simplest iterators are strings, so that's mainly what the documentation uses to demonstrate the itertools functions. But remember that these functions work with any kind of iterator, not just strings. And the first group of functions, like utility functions, we'll look at includes relatively simple functions that you typically use to provide input to other functions in the module. There is a count function that works a lot like the built-in range function, except where range generates numbers up to a limit. Count generates an indefinite series of numbers from a start point, incrementing by a given optional step size. And let's have a look at how count works. Okay, guys. Sometimes in PyCharm the Python console acts up a little weird sometimes. But if you go to the Python interpreter in command line or in terminal, the same code that we wrote earlier, it should work properly. So I'll just show it in this in command prompt instead. Sometimes the Python console is not working properly. I don't know why. So okay, at least this works. It does a starting point of 15 and a stepping and a step size of 2. So up till 40, we print the n value, and it stops at because it prints up till 40. So we have another function called repeat, and the repeat function is even simpler. It just repeats its arguments continuously or for the number of repetitions specified. Let's look at another example, and I'll use the interpreter in command prompt. Just like that. And one note that several of the itertools functions produce a potentially infinite series of output data. This has the potential to lock your program into an infinite loop, so you need to take extra care to ensure you provide an exit mechanism when using these functions. And then we have another function called cycle, and the cycle function rotates over the input sequence over and over again. This is useful for building round-robin style iterations for load balancing or resource allocation. Consider the case where you have a number of resources and you want to allocate data to each resource in turn. You can build resources, then cycle over that list until you run out of data. And we can simulate this technique using list as resources. Let's try that out. Should be inside parentheses. Excuse me. Typos are part of programming, as you can see. So just a typo here. have to retype the whole thing. Just 1 second. So, oh, I didn't need to retype. I just had to access the lists, and it has filled out the list as needed. And the chain function, we have another function called chain, and the chain function concatenates all the input arguments into a single collection and then returns each element. If the arguments were all of the same type, you could achieve the same result by adding the collections together with the plus operator. But chain also works for types of collections that are not compatible with the plus operator. So let's try it out with an example using a list, a string, and a set. And always, guys, if you didn't understand what I was doing, please always go pause the video or just go back and watch it again. So that's the chain function of itertools. And finally, there is a slice function that works like the slice operator, but because it uses a generator, it's more memory efficient. It does have one significant difference from the normal slice. You cannot use negative indices to count backwards from the end because iterators do not always have well-defined endpoints. And we can use a slice like in this example. That's the stepstone. This is the start point, end point, and step size. So it does the same as slicing. So itertools can do much more than just generate data. It can also help analyze data using a variety of data processing functions. And data processing functions. itertools has many data processing functions that either take input data and transform the elements or filter the contents in some way. By combining these functions, you can build sophisticated data processing tools. One feature that many of these functions have in common is that they accept a function object as a parameter. One note is that passing functions as arguments in a common feature of functional programming style and can seem a little strange at first. You need to remember that in Python, a function is an object too. a function name is just like any other variable. It is simply a reference to a function object. As such, you can pass a function name such as f, for example, into another function, say g, and function g can call the input function f internally. Functions that return a Boolean results are often referred to as predicates. And we have another function called compress, and the compress function acts like a little bit like a higher order version of the bit masks that we explored in chapter 1 and 2. It takes a collection of data as its first argument and a collection of Boolean values as its second. It returns those items of the first collection that correspond to the true values of the second collection. So let's try it out with a basic example. Note that the Boolean values do not need to be pure Boolean values. They can be anything that Python can convert to Boolean, even expressions. And the itertools.filterFalse function, I'll just write it down so you understand what I'm talking about. This function works in exactly the same way, but in reverse. It returns those elements whose corresponding Boolean flags are false instead of true. And likewise, we have another function called dropWhile and takeWhile. The dropWhile and takeWhile functions have related but opposite effects. Both take an input function and a collection or iterator as arguments and then apply the function to the input data elements one at a time. dropWhile ignores all of the input elements until the function argument evaluates to false, whereas takeWhile returns the elements until the result is false. So we can see the difference by typing something in that uses the same input data and argument functions. Do I have a one parenthesis too much? No. So note that both of these functions stop processing the data after the first time a trigger is detected. So let's consider another example. So notice that the output includes the single-digit numbers following the first non-single digit number for the reason just indicated. Once drop while stops dropping, nothing else is dropped thereafter. And take whilst taking behaviors is analogous. And there is another called the accumulate function. And the accumulate function applies its input function to each element of the input data along with the result of the previous operation. The default function in addition and the first result is always the first element. Thus, for an input data set, let's say 1, 2, 3, 4, the initial value result 1 is 1, followed by the function applied to result 1 and 2 to produce result 2, and to result 2 and 3 to create result 3, and to result 3 and 4 to create result 4. The output is result 1, result 2, result 3, and result 4. The final result value is the same as applying the reduce function from the functools module. So let's try to use accumulate function. So also there is another function called GroupBy, and GroupBy is one of the most useful and powerful of the itertools functions, but it has a number of little foibles that can catch you out. Its basic role is to collect the input data into groups based on a key derived by an input function and return those groups as iterators in their own right. The first problem is that the function only groups for as long as it finds the same key, but it creates a new group if a new key is found. Then, if the original key is found later in the sequence, it creates a new group with the same key, rather than adding a new element to the original group. To avoid this behavior, it is best if the input data is sorted using the same key function used by GroupBy. The second snag is that the groups generated by GroupBy are not really independent iterators. They are effectively views into the original input collection. Thus, if the function moves on to the next group of data, the previous groups become invalid. The only way to retain the groups for later processing is to copy them into a separate container, a list for example. To reinforce this concept, we look at an example that produces a set of data groups that can be processed independently. The example is built up to the final correct solution, starting from an initial but broken solution. First, we'll just define several groups of data and use the built-in all function as key. The all function returns true when all of its input data items are true. So let's start to type in the example. So next we apply the GroupBy function to our data. Let's just use this not to. And we can see that GroupBy returned two separate groups, both keyed on true. To avoid that, you must sort the data before processing it with GroupBy. And we can use it by doing this. And as you can see, fault set is empty. That's because the fault set group was created first and then the underlying iterated group moved on, thus invalidating the value just stored in fault set. And to save the sets for later access, we need to store them as lists. So notice that we created a dictionary whose keys are expected once, true and false, and host values are lists. We then had to append the groups converted to lists as we found them. This may seem complex, but if you remember to sort the input data first and copy the groups into lists as GroupBy generates them, you'll find that GroupBy is a powerful and useful tool. And now let's try to use itertools to analyze our lending data that we used from earlier, this lending_data file. So what we are going to do, you've seen that itertools has to offer what itertools has to offer. So now it's time to try using it with our lending_data.py file. We want to repeat the analysis that we did using the standard tools, but see how the itertools function can be brought to bear too. Remember, the real point of the itertools module is not so much that it gives you new features, but rather that it lets you process large volumes of data more efficiently. Given the tiny amount of data we are using in this lesson, we won't actually see any efficiency improvements, but as you scale the data volumes up, it does make a difference. So let me just clear out everything here. So we do a fresh start. Import all from lending data. Import all from itertools. To answer the question, what is the total cost of all items? And to answer the question, what is the average cost of an item? And to answer the question, who contributed the most items? These are examples from earlier, but with itertools now. To get all the brackets. commas. There's one parenthesis missing here. I think this is a parenthesis. Yep. It's a parenthesis. I'll explain in a minute. Member. And the final question is which items are currently on loan? Just have to get the right parentheses and brackets. So, as in the previous example, we created a small helper function to improve the readability of the code. To answer the first question, we used the accumulate function to produce a running count of the costs. Then use isSlice to extract only the last item by specifying a start index of len items -2 and a stop index of none. We had to subtract 2 to account for the headers line at the start of items because the result n was still in scope. You could calculate the average by simply dividing n by the number of items. The question of who contributed most is answered quite differently from the previous example because we use GroupBy to gather the related items. In this case, you are interested only in the size of the group, not the details. So you use len function to calculate the size of the group. We then iterated over the members in conventional style to print the names and counts. And we answered the final question by inverting the logic of the helper function returned to return whether an item has been returned by using that in the filter false function. You could find those items that had not been returned and therefore were still on loan. So in this lesson, we have now seen a mix of conventional Python data structure, functions, and operators combined with the functional techniques of the itertools module, and how that enables you to perform complex analysis of quite large data sets. However, there comes a point when the volume and complexity of the data call for another approach, and that means introducing a new technology, relational databases powered by the SQL language, which is also short for structured query language. That's what we are going to look at in the next lesson. So I hope you enjoyed this coding techniques so far, and we'll start the next lesson of managing data using SQL in the next lesson. So see you then.